Well, students, we now come on to the discussion of Wheatstone Bridge. Now, fundamentally, we should know that this Wheatstone Bridge is used. Purpose of using the Wheatstone Bridge is to determine unknown resistance. So this is actually the bridge which we use to find out unknown resistance. So this is the purpose fundamentally. And if you can calculate unknown resistance, then you can find many other things. The Wheatstone Bridge is also used to apply. This is also an application of KCL and KVL, which we have just learned. That KCL stands for Kirchhoff's current law and KVL stands for Kirchhoff's voltage law. So fundamentally, applying these two laws, we are going to find the unknown resistance for a Wheatstone bridge. Now, let us come to that part. Well, I will first draw the bridge. The bridge should be drawn very neatly. Otherwise, it's very difficult for us to understand that what's the current and all that going on. So this is the resistances of the bridge. Now this resistance is the first arm resistance called P, the second arm resistance called Q, the third arm resistance called R, and finally this is the unknown resistance, the fourth arm, which is S. And there is a galvanometer here which reads current fundamentally, which is connected across these two ends. So this is my point A, this is my point B, this is my point C, and this is my point D. Now I start with KCL. I begin with current I. Let this be the current here, which is I1. So what I have here is I2. Now the current that is passing through this galvanometer is Ig. So I hope, students, you can get that this current can be nothing other than I1 minus Ig according to Kirchhoff's current law, because this is I1, Ig gets out. So what comes in here? I1 minus Ig. I hope you can remember that this is 10, 8 goes, what remains? 2. So that is exactly what we are doing here. So now as you can see, Ig is coming from here, I2 is coming from here. So what gets in here is I2 plus Ig. I hope this is also clear to you that I2 plus Ig gets in here. And if you can calculate the current here, I hope you can get it that this is I1 minus Ig and then plus I2 plus Ig, which happens to be I1 plus I2, which happens to be I. So this is application of the bridge as far as the Kirchhoff's current law is concerned. So this is the application of the bridge with aspect to current's law, and now we'll go to the KVL part of the bridge, where we apply the voltage law. So now let's get to the voltage law. Now for the voltage law, what we are going to show here is again the resistances along with the currents that we already have in the various arms. So this is the circuit for us. I hope you remember that this current is I1, this current is I2, this current is I2 plus Ig, and this current is I1 minus Ig, and this current is Ig. And this is my loop 1, this is my loop 2. So now let me write loop 1. You see, as I am going from this direction to this direction, and I will note the points also A, B, C, D, so that will be easier for me. So loop 1, as I go from this loop, you see, as I go from A to B, the direction in which I am going, because I am moving in this direction clockwise. So this is the direction of the current as well. So this is plus. So the resistance, I will write the resistance here. This is P, this is Q, this is R, and this is S. So let us put it here as I1P. Then as I can see, the current goes here. I am also going here, and the current is going here in the same direction. So it is Ig into G, where G is the resistance of the galvanometer. Now, when I am going in this direction, the current is coming from the opposite direction. So it should be minus I2R. So this is my equation 1. And now for loop 2. As you can see, for loop 2, as I am moving in this direction, the current is also coming in this direction. So I have to write it plus. So it is I1 minus Ig into Q. As I am going in this direction, the current is coming from the opposite direction. So it is minus S I2 plus Ig. As you can see, I am going in this direction. The current is coming from opposite direction. So it is minus Ig into G is equal to 0. And that is equal to the second equation. Well, I have to put it as 0 here. That is equal to 0. This is the first and this is the second. Now, what happens actually for a balanced bridge is that no current passes through this galvanometer. This is a condition of the bridge, what we call the balanced condition. The potential at B is equal to potential at D. So, this is what we call about the balanced condition of the bridge. The moment these two potential become same, Ig happens to become 0. As Ig becomes 0, as you can see from this equation 1, we can write it I1P is equal to I2R. And from this equation, as Ig becomes 0, as you can see from here, we can write I1Q is equal to I2S. And then if I divide these two, I1P, I2R, I1Q, I2S, if I divide these two, I get the balanced condition. So I'll try to write them and give you the final form correctly. So it is I1P is equal to I2R, and it is I1Q is equal to I2S. So if I divide these two, what I have is P by Q is R by S. So that is what we call the balanced condition of the bridge, which can be derived applying KCL and KVL. So that is what we are doing. I will repeat again. The first equation is I1P is equal to I2R, and the second is I1Q is equal to I2S. And then if I divide them, I get P by Q is R by S. This S is unknown. When P, R, Q, the resistance in the first term, the second term, the third term is known. The resistance in the fourth term, the unknown resistance in the fourth term can be easily calculated. So that is all about Wheatstone bridge and how it is solved applying KCL and KVL. Thank you, students. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.